magnified view of the star Sirius. In 1844, Bessel, and he watched the wobbles of Sirius, and he said there has to be something, a companion to Sirius that we're not seeing, because that's what's making Sirius wobble. He couldn't see it with the telescopes they had at the time, but it was this inference, which we'll use again and again, that we see something moving not according to Newton's gravity, but doing something else, and that suggests that something's wrong. Newton's theory's right. That suggests there's something else there. And this is a fairly modern picture of the companion of Sirius, which is shown by the arrow. And they're called Sirius A and B. The brighter one is A and B is the fainter one. That was actually discovered by an American astronomer, Alvin Clark, who worked in the 1870s and built excellent telescopes as well. He had a factory to manufacture telescopes, but he and his family also did some astronomy. And one of the Clarks took the first image of Sirius B. And Clark, by the way, was also the person who designed and built the lens for the refractor on Mount Hamilton. So all kind of a connection there.
Roger, could you maybe hit OK and then the X? Maybe you're blocking out the
two more things at the top.
Yeah, blocking out the titles.
You can hit a little X on that box up.
Okay. Okay.
And then the
And the X. There you go. Yep. All right.
You're fine.
He
needs to see his notes.
So now that stopped. I can't make the slides work again. There we go. Okay, now it works. Okay, well, Sirius B does an orbit around Sirius A. And this shows the orbit. It takes it some, 50 years or something like that to get around. And so I guess we're up at 2025 right now. It makes this orbit, which is the elliptical orbit, which Newton predicted. And from that orbit, we can calculate the mass. It's a little complicated, but knowing what kind of a star Sirius is, and then from the orbits, we can calculate the mass of Sirius B. And we can also measure the temperature, the surface temperature, just from the spectrum, and we can measure the brightness, how bright it is, because we know the distance. Sirius is actually a very close star to us. So from all of that, it was deduced that Sirius B is really an incredible star. First of all, it is approximately the size of the Earth, but it's the mass of the sun. So it's an incredibly dense, heavy, massive thing. And the temperature is about 20,000 degrees. So it's extremely hot. The sun, remember, is 5,800 degrees, something like that. 25, so and that's why it's called a white dwarf. It's a small star and it's white hot. So this was an amazing thing, and let's try to imagine this. I mean, this is, I've shown that picture before. If you compress that whole sun into something the size of the Earth, what kind of an object that would be. Now, I'm just going to make you learn one thing. It's when I'm going to have to talk a lot about masses and sizes of stars and black holes and objects. Now, I don't want to talk in grams or pounds or slugs or something like that. It's too hard. What I'm going to do is to compare to the sun. Now, the sun has a mass that's hard to imagine also, but at least it's something familiar that you see. And the sun is kind of an average star. Sorry to tell you that. There are bigger stars and littler stars. We're kind of just average, okay? So it's an average G2 dwarf type star. It's fine. And so I'm gonna denote that by a solar mass. And so, for example, a star that's 6 times more massive, I'm going to call it a 6 solar mass star. Make that kind of comparison. Otherwise, in grams, the sun weighs 2 times 10 to the 33 grams, 2 with 33 zeros after it. And that would be hard to talk about, right? So this is a good way to put it. All right, so sun's familiar. This is a neat picture I like of Pharaoh worshiping the sun. Stop. Oh, there it is. Okay, well, this mass is really something else. A teaspoonful of this would weigh about 110 tons. Okay, so about the same as a train. So 1 teaspoon of white star matter weighs as much as a big heavy train.
What kind of spoon would hold that?
That got a good laugh. Okay. All right, but you've not seen anything yet. All right. So, what does this? And people were puzzled by this and wondered about it. But in the 1930s, Chandrasekhar came up with a theory which explained what the white dwarfs are. And he said that the white dwarfs are the end states of some stars, particularly stars like the sun, that stars evolve in time towards a white dwarf. And the white dwarf is largely made of heavy elements, carbon and I'm going to say here, iron, and furthermore, it's held up not by the normal pressure like the sun's is held up, but by a quantum pressure, which is I can't go into, but it's held up by quantum physics, which prevents the electrons in the star from getting too close together. And furthermore, he also said the star has, these white dwarfs cannot be more massive than 1.4 times the mass of the sun. Because if they're more massive, they'll just collapse. That process only happens up to 1.4 solar masses. Weird. Well, that was a whole new theory. Nobody had ever seen it before.
Roger?
Yeah.
Is that a pressure from the outside, or is it an inside?
It's inside. The electrons, you try to put electrons too close together into the same state, they resist doing that. It's a quantum effect that has no classical analog, but it's the same thing that keeps atoms from collapsing onto themselves. It's the same reason why the atoms in iron, the electrons that circulate the iron nucleus don't fall into the nucleus. They just can't. It's a quantum effect. Okay, and I forgot. Okay, oh wait. Oh no. This technology is not yet perfect. Okay. I'm not perfect. Well, this started a big controversy, and Chandrasekhar was a young scientist at the time, and the most eminent astrophysicist in the world, Arthur Eddington, one who measured the bending of light, said it was wrong, that he couldn't believe that. And he criticized it very strongly, which caused Chandrasekhar, as a young scientist, a lot of pain. But Eddington didn't have an alternative. He says, I think there should be a law of nature to prevent a star from behaving in this absurd way. Well, okay. Well, Eddington was wrong. And Chandra won the Nobel Prize later for this work. And this is a spacecraft named after him. I did have an interaction myself with Chandrasekhar, although it doesn't put me in the very best light, I guess. Is this going to go out on the web? Oh, well. The second paper I ever wrote in astronomy as a grad student, I submitted, and at that time Chandrasekhar was the editor of the Astrophysical Journal. And in the paper, the way the Astrophysical Journal worked at the time was that for a reference to some statement you make that you didn't find yourself, but you wanted to refer to where it came from, or some thought, the way you did it was that you made a statement, then in the text, you wrote the name of the author of the paper and the date. So it would be like Smith, 1952, would be in the paper, and then at the back of the paper, there would be the references, Smith, 1952, an Astrophysical Journal, journal number, date, pages, and so forth. Well, I made a mistake, and I got the date wrong between the two. I wrote 1951, and in the references it was 1952. And I didn't catch it, and the people I gave the paper to didn't catch it, and the reviewers didn't catch it. And Chandrasekhar caught it. And in red ink, he circled the two dates, and he wrote to me on the paper in red ink, "I hope the science in this paper isn't as careless as the reference." Well, that had the desired effect.
That means you got an A minus?
Yeah, okay. Comment?
Well, just a quick question. When the Sirius was so bright, does it have an effect on the Earth's temperature?
On the
Earth, yeah, but well, like the sun. The sun, it's the energy. What happens with the energy? Does it affect us also?
Does it affect us?
Yeah, on Earth.
No, it's very small compared to anything. I mean, you see the star out there.
Yeah. So it has no effect.
There's no effect.
Roger, more screen tending. Roger, another okay up there.
Oh, yeah. Go through all that.
Your comment is not being transcribed. Congratulations.
Maybe we should erase that.
Good.
All right. Let me just give a brief overview on how this happens. This is a cutaway view of our sun. And the major thing to note here is that the energy of the sun, what makes the sun shine, all occurs in the inner core 10% of the sun. And the process is a nuclear process primarily of the conversion of hydrogen into helium. The sun is almost all hydrogen and helium. Hydrogen dominates, over 90% of the atoms are hydrogen. And the conversion of hydrogen to helium in the center of the sun, where the temperature is about 15 million degrees. And that's hot enough for nuclear reactions to happen. That, by the way, is one reason it's hard to get fusion reactions to go on Earth. You have to get up to that kind of a temperature. In fact, for what we can deal with, even somewhat higher, and that's very hard to do. Most of everything melts at 15 million degrees. So all right, now, what happens, this thing starts and stops. So no, it did it. Look at this. Maybe there's a time thing. Anyway, to make a very long story short, once the hydrogen in the core of the sun is largely depleted by the conversion to helium, then there are also other reactions that make carbon and oxygen. The sun converts into a red giant star. And that star has the carbon and oxygen in the core, but has a shell which converts helium into heavier elements. And it shines that way. But that's going to happen to our sun in about 5 billion years. But when it does, it will change things a lot. Because while the core contracts, it burns very brightly, and it expands the envelope around it. So the star expands enormously, and you see it would go beyond the element of the orbit of Mercury, way out here. And other models, and these things are very variable and they change, and other models have the red giant coming almost to the orbit of the Earth. And so that then the surface of the Earth will be roughly the surface temperature of a red giant will be, which is about 3,000 degrees. That's 5 billion years from now. But focus on the core, because the next thing that happens, well, by the way, Betelgeuse is a red giant star, the red star in the shoulders of Orion. And you can see that color. We say it's red, you'd probably say it's orange or yellow or something, but it's a red giant. It's that star. So you can see those colors with the naked eye. And the next step is that the star blows off the big envelope. And this is an example of it. This is the famous Ring Nebula in Lyrae. Some of you may have seen that with amateur telescopes. This is a JWST photograph, which shows it much better than anything. And you can see that this star in the very center has blown off much of its envelope. And the red color is hydrogen emission. The green is probably oxygen emission.
Does that happen suddenly, or is it just a gradual?
It happens pretty suddenly astronomically, thousands of years, for example, and it can happen repeatedly.
Oh, it oscillates?
Different, you can keep pushing it off. I didn't, my hands oscillated, but I didn't do that. Okay. No, it doesn't advance at all. Can you tell me what's going on here?
I think it's because you're over that little doodad there, like this green. You go over your slide.
Yeah, okay. Yeah, you're right. Here are some more. They're called planetary nebulae, but that's just a historical name. When in the 19th century, when they saw these nebulae and they were roughly green colored and so on, people thought they looked a little like planets and they weren't sure about it, but the name is stuck. And so you can see some of them have multiple events. And I don't know, the bottom right, which is a JWST photograph which just came out, I don't have any idea how that works, so somebody's going to have to explain that. So, in summary, this is the evolution of a star. And a star forms out of the interstellar medium, out of the clouds and dust and gases. They're in the interstellar medium. It condenses, forms a small star like the sun in this instance. Eventually, after billions of years, it forms a red giant. Then it spews off the envelope of the red giant, and it becomes a white dwarf. So it is a property of stellar evolution.
And it's the gases in the nebula, does that become the basis for new stars or planets forming?
Yes, the question is, are the gases in the nebula the basis for new stars and planets forming? Absolutely. That is exactly what happens. And in fact, in the beginning of the universe, when the universe was primarily hydrogen and helium, then the first stars started forming carbon, oxygen, nitrogen, and the heavy elements. And that's the kind of stuff that we formed out of. That's where it came from. So it's a continual evolution. The universe is getting richer in the heavy elements, but very slowly. One more question? Yeah.
The mass of the white dwarf that you said was much larger. If it has expelled stuff, where did the extra mass come?
Yeah, well, the stars in a range of up to about 8 times this mass of the sun can form white dwarfs. Okay, so the white dwarf that we're seeing in the Sirius B, which is about 1.07 solar masses, something like that, formed from a heavier star than our sun is. But they range in mass, Okay, I just gave the Sirius B one. But the white dwarfs range in mass up to 1.4 solar masses. We've never found a white dwarf more massive than 1.4 solar masses. Chandrasekhar was exactly right. Okay, so just to review it, the end states of solar type stars. The densities are in the order of a million grams per cubic centimeter. Remember, water is 1 gram per cubic centimeter and steel is about 8. These are a million. They're about the size of the Earth, but with a mass comparable to the Sun. And this is going to happen to us in 5 billion years. But we won't be around to see it even. So. And there's a maximum mass of 1.4 solar masses. So, but this hinted at even something more, because people ask, what happens if there's a white dwarf that's more massive than 1.4? What kind of an object is that? And there was a remarkable paper by these two physicists, Zwicky and Bode. In 1934, they wrote a paper which said that stars can undergo titanic explosions, which they named supernovae, and that the remnant of such a titanic explosion would be a star made not of the iron and oxygen and so forth and carbon of white dwarfs, but and the electrons, but made of neutrons. Neutrons are the particle in the nucleus with the protons, which make up the atomic nucleus. And they said it would be such a dense object that basically the electrons and the protons would be squeezed together, negative and positive particles, and make neutrons. They would have incredible densities, and the whole star would be as dense as an atomic nucleus. An amazing thing, amazing paper, and it wasn't ignored, but people didn't know how to test it very well, and Zwicky himself was he looks very pleasant there, but he was a very strange character. He got into these fights with people which were almost frightening, and in fact, they did this fundamental work, and about 5 years later, Zwicky got angry at Bode, and Bode said, "I think he's going to kill me." You know?
Oh, geez.
So here's a supernova. Some stars explode, and explode with tremendous violence. And here's a before and after picture of a supernova going off in a distant galaxy. One star in a distant galaxy exploding and forming this supernova. And
Back again, bent back another one.
I'm going to give up on this thing. And it's maybe not as dramatic as it might be, but just you have to think of this. That galaxy is somewhat similar to our galaxy, 200 billion stars, 200 billion times the brightness of the sun. And yet one star in that galaxy puts them all to shame for a brief period of time.
Was that what?
It's a horrible, massive, unbelievable explosion.
Was that what Krakatoa was?
No. That was about it. Here is the remnant of one of these explosions. It's, of course, very different from the planetary nebulae I showed you. But this supernova went off in our galaxy in 1054. Wow. And it was recorded by Chinese astronomers who said it was visible during the day for more than 2 weeks.
Wow.
And today, and we know that, well, the Chinese told us approximately where to look, and we looked there, and there it is, and then you can measure the speed of these gases moving out. And if you make the simplest assumption that its speed hasn't changed much, it's going to take about 1,000 years to get out here. So this is the remnant of supernova 1054. For some reason that I've never understood it, it was not recorded anywhere in Europe. But you know, the climate in Europe might have been cloudy for 2 weeks or something like that. I just really don't know. Or we lost the records.
But it was in 1054 when we were in the Dark Ages, Europe. To check.
Sorry?
The date that they recorded it is.
Was 1054, yes.
Yeah, well, our sort of knowledge started to increase after that, didn't it?
Well, you could say that, but there are, for example, we did get a good record of the comet of 1066. And so people were looking at the sky and people were recording things. Halley's Comet came in 1066.
Roger.
Yeah?
So if 1,000 years ago that was smaller, was it also that much brighter?
Yes, I mean, it was a hugely, now it's a nebula that's fairly easy to see with a small telescope, can't see it with the naked eye. But when that supernova went off, it was a bright star. It was the brightest thing in the sky for 2 weeks. Here's one that went off very recently, close to us, in the Magellanic Cloud. Magellanic Clouds are little galaxies that are outside of our galaxy, but that gravitationally attached to our galaxy. And you can see the before picture and the after picture. Blasted away.
So Roger,
Yeah?
when you say that it was seen in 1054, but we also talk in light years, when did it really happen?
Yeah, that's the distance. If I remember correctly, the distance to the Crab Nebula is about 1,000 light years. Okay, so it happened there. It happened then. So it took 1,000 years for lights to get here. What we see now is happened 1,000 years ago.
Right.
If I remember the distance correctly. Well, the result of a supernova explosion is that it removes the envelope of a very massive star. And stars greater than something like 8 solar masses will not end as planetary nebulae, but will in fact explode as supernovae. And the remnant of that event is a neutron star, which turns out to be about 10 kilometers in size. So roughly this is how big a neutron star would be. And it's still a solar mass. So now it's even more dense. Well, that was theoretical for many years until 1967, when Jocelyn Bell and Tony Hewish saw something strange in their radio observations. They saw not a continuous radio signal that we get from most radio sources, but they saw these pulses, which you can see here at the bottom. Pulse, boom, 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 at 33 times a second, approximately 33 times a second. This isn't a crab pulse. So very fast pulses. And they saw this in roughly the summer of, I think there's a date here, 1967. And Jocelyn was the first one to notice it when she was at the telescope. And she saw this, and they were amazed. The first thing they thought, of course, was, is it little green men? Is it people broadcasting to us? Turned out, for various reasons, they could rule that out fairly quickly. And Hewish and Bell then published it and called it a pulsar, published this data. Now, remember when this came out, people were very puzzled by it. But it quickly became clear because their first pulsar was not the pulsar in the crab, but there is a pulsar in the crab. The central star in the Crab Nebula is a pulsar, it's pulsating at 33 times a second. So here you can see the images of that star getting brighter and fainter. So this pulsar pulsates in the visible as well as in the radio. And I think I have a strobe picture of that. Okay, and now you see these stars are wobbling, but that's just the atmospheric scene, looking through the atmosphere. But this one is pulsating. So here's a solar mass star, which is turning on and off 33 times a second. Can you imagine that? A solar mass turning on and off 33 times a second. So our understanding of this is it's a rotating neutron star, which has a bright patch on it. And it's rotating around 33 times a second. It's absolutely amazing.
Is that frequency unique to that one, or is that uniform with all the?
It's unique to that one. But they all vary very quickly. They all go very quickly, but they vary from 1 to, I don't remember the total range. Well, you can, from that, rotating that fast, okay, just think of it as a merry-go-round going around. The faster you spin it, the more you have to hold on to it, right? The harder you have to hold on to it. And this is the same with that pulsar. It's a neutron star, but if it's to hold together a solar mass rotating 33 times a second, there has to be enormous gravitational force holding it together. And that means it's enormously compact and massive. Okay. So that's how that works. And that was the first solid evidence for a neutron star. And Hewish got the Nobel Prize for this, but Jocelyn didn't. And that was very controversial. And most people think both of them should have gotten it. She did see it first, and she did continue working on it to try to understand it. But on the other hand, Hewish had, it was his idea to build a telescope and design a telescope and get the money for it that could see very fast-paced things. So he was behind it all and hired her as a grad student, and she saw it first. So I don't want to argue about who should have gotten the prize. Anyway, he did and she didn't. So that was kind of controversial.
Was it ever determined why it pulses in the first place?
What we're certain of is that there's a bright spot on
Can
it.
you repeat the question?
And yeah, the question is, was it ever determined why it pulses? The pulsar has a bright spot on its surface, and as it rotates, the bright spot keeps coming by us.
Are there theories about why it would just have a single spot that's bright?
Are there theories why there are single spots that's bright? I've never seen anything like that, nor that it's even true, that they all of them have just one spot. Okay, some of them don't have any spots. Or bright areas. So I don't think that detail has been really worked out. We don't have perfect models of neutron stars. All right. Well, here's a picture of one, maybe. And I added the red dot to make the spot there, actually. So that's the answer. I added it. It's 10 kilometers in size. And again, this is maybe what it would look like. And the masses of them go up to about 2.3 solar masses. So they are heavier than white dwarfs, but they also have a limit. That limit is not perfectly known, but it's somewhere 2.3 to 3 solar masses. And the surface temperature is over 1 million degrees. And it gets hotter inside.
Jeez.
So they're unbelievable things. And now a teaspoon of neutron star matter would weigh about 1 billion tons. See, because before the white dwarf, remember, was the size of the Earth. Now we've got one that's the size of Santa Cruz or so, or a little bit bigger. And that means the density goes up again enormously. And so a teaspoon of this matter would be about as much as Everest.
So different spoons.
Yeah. I always like to sneak in a picture that from my travels and vacations, and And I got this one in by some effort. So I took this picture. And so it's a very strange, massive kinds of matter.
You took the picture of the spoon? Sorry.
We got a lot of comedians today. He said, I took the picture of the spoon. Yeah, sure. I took the picture of Everest, but I didn't climb Everest or anything. I don't have any much stories to tell about that. All right. The Chandra spacecraft has taken some really great images in the X-rays of these things. And here's another supernova remnant. And you can see the neutron star in the middle. And this is actually the Crab center. That's a total mystery to me. I can't even use it as a pointer anymore.
Yeah.
But you can see in the center of the Crab, and these are X-rays, so it looks different from the visual. But the star is about here. So those are neutron stars.
Now, do all neutron stars pulse?
Pardon?
Do all neutron stars pulse?
I don't think so. I don't think that's known. They have to have this hot spot, but we don't have a way of finding it without the hot spot. So here is now another path of evolution of stars. Again, we start with a nebula, and now we make a large star, larger than the sun. Its initial mass is greater than the sun, 8 solar masses or more. This then does form a red supergiant, but instead of shooting off its material kind of cohesively, it explodes violently, and the remnant is a neutron star.
So is what distinguishes which path it takes the initial size of the star?
That's accidental. It depends on this. Yeah, okay. What determines the mass of a star, I think is your question.
No, if it goes through the evolution from a nebula to a supernova,
Yeah.
and the other one goes through evolution into a planetary nebula and then becomes
A white
a white
dwarf.
dwarf. What determines which of those two paths it takes?
What determines
Is it the
which?
initial size of the star?
Yes. Question is what determines the two paths, and the answer is that it's the initial mass of the star. Stars form at different masses. Our star is an average star. Most stars are actually much smaller than our star. Many stars are much more massive than our star. And that what determines the initial mass of a star is a complicated thing, and it has to do with the initial conditions in the nebula. What are the conditions in that nebula? You know, is it initially dense? Are other things pushing on it? So forth. And so it's a probabilistic thing, like what determines the mass of a planet. It's a probabilistic thing, and those which happen to get massive initially end up this way.
Okay.
So it's all determined by the initial mass of the star. Good questions. Okay, so this is another thing. End states of stars more massive than the sun. Densities in the order of 1 billion times, 10 kilometers in size. The fate of stars greater than solar masses, we think, but it's pretty complicated. And the maximum mass of a neutron star before collapsing under its own gravity is 2.3 times the mass of the sun. It might be a little bit more than that. The theorists are still working on this. Okay, so the next question is, of course, what happens if it's more than 2.3? Okay, let's take a break. Part of the class, I will start by talking about some theoretical background and then get into the observations. In 1916, Albert Einstein published the theory of general relativity. We talked about that a little bit. Of course, it was a newer way to look at gravity than after Newton. And the new way to look at it was that gravity was really a force that we infer, but the basis of it is really the curvature of space-time. I got this picture of Einstein supposedly talking about general relativity, and that was their caption. But if you look at the blackboard, it's really special relativity that's on the board, so I'm not sure that's completely right. Okay, now Einstein published this in 1916, and a few months after Einstein published it, Carl Schwarzschild took this theory of general relativity and solved this problem. How would the general relativity predict the curvature of space around a spherical object? It's sort of almost the simplest thing you can think of. Like the simplest problem in Newtonian gravity is, what's the gravity of a round spherical object? It's symmetric, it's easy to do mathematically. Carl Schwarzschild did this problem for Einstein's relativity. It wasn't an easy problem, but he solved the problem and showed that that there could be conditions in which the mass is so compressed and so small that nothing, even light, could escape from it. And it was a remarkable achievement. Well, for one thing is, Schwarzschild at the time was a soldier in World War I, and he got in Russia, and he was extremely ill, and he worked this out while he was in the hospital in Russia, and he died a few weeks later, a few months later. So he was and the other thing about Schwarzschild was it's not as though he was drafted or anything. He was a very renowned astrophysicist, but he volunteered over the age of 40 to fight in World War I. So it was a kind of an amazing story. It did it almost by itself. Well, here's the kind of prediction we have. I'll go into this a little more. But imagine now a sphere, very small sphere, and if you get within a certain distance, we call this event horizon, then nothing can escape. So in terms of the picture we had of the two-dimensional picture of a gravity with the sun and so forth, in the black hole in space-time, the Schwarzschild radius thing is something like out here, but the calculation showed that the space would keep contracting infinitely small in the center.
Roger,
You get an infinity.
the neutron star, I mean, the white dwarf has a maximum mass of 2.4. The neutron star has a maximum mass of 3 point something. Is that the mass where gravity is so strong that light cannot escape? Do we know?
Yeah, you're stealing my thunder here.
I'm sorry.
You have this. The question was, you have this white dwarf up to 1.4 solar masses, and you have the neutron star up to 2.3 to 3 solar masses. What happens? More massive. That's what I'm talking about now.
Okay, sorry.
All right. So the Schwarzschild. So we have something called the Schwarzschild radius. So you have this extremely massive object, and at each mass, say a solar mass, 10 solar masses, 20 solar masses, they all form a horizon which is dependent upon the mass of the object. That's called the Schwarzschild radius. That's what we calculated. So let's see, where am I? Oh yeah. Now you can ask, what is the Schwarzschild radius for the sun? If you made the sun into what I'm going to now call black holes. By the way, the term black hole was not clear who first came up with it, but Wheeler at Princeton popularized it in the 1960s. So Einstein, Schwarzschild wouldn't have known what to do with black holes, with the term, but anyway. So the question is, what would have to happen if the sun were to contract into a black hole? How big would it be? Well, the answer is it would be about about a Schwarzschild radius of about 3 kilometers.
Wow.
So it would be about this size. This would be a black hole inside.
Right on our house.
So it's an extreme
would
thing. Now, I want to quickly, I want to give this as an example because it's something familiar, but we know of no black holes this small. They may exist, but we don't know of any. All the black holes that we've been able to detect so far are more massive than this. Oh yeah, did I lost it. Okay. So you didn't want to be close to a black hole. A good rule for living is don't get too close to a black hole. All right. Now remember, we have we showed last time that light would be bent, and so light near a black hole would do lots of strange things. If you get fairly close, light would be bent, but if you get really close, light could actually orbit the black hole. Light could go around in a circle around the black hole, or it could even collapse and go into the black hole. So, but the question was, after this work, and this was 1916, do they exist? Do black holes exist? And there was a lot of objection to this. And in fact, I think, Albert Einstein didn't think that this would work. And he said, the essential result of this investigation is a clear understanding as to why the Schwarzschild singularities do not exist in physical reality. Schwarzschild singularity does not appear for the reason that matter cannot be concentrated arbitrarily. But he was wrong. Can't. I don't want to, Einstein wasn't always right about everything. I mean, he's a genius, mythical genius, but he could get off sometimes. Well, the next step was another theoretical step when Oppenheimer and Snyder in 1939 did try to calculate what happens to stars greater than 20 to 25 times the mass of the sun. And they couldn't find any way that you could prevent a collapse, total collapse. Nothing could stop an object contracting if the initial mass was that high of the star. And this was another strange kind of event. In 1939, this kind of astronomy was not in the forefront of science. So the paper, as far as I've been told, didn't attract too much attention, but it was very fundamental. And then, of course, this is the same Robert Oppenheimer in the movie, developed it, was the leader of the atomic bomb project. And a strange thing happened that after the atomic bomb project, Oppenheimer became the head of the Princeton Institute for Advanced Research, which had Einstein and Gödel and other really big shots in it. But Oppenheimer seemed not to be interested anymore in the subject. And when people asked him about it, he shrugged it off. He seemed to think it was not something really important that he had done. And Freeman Dyson, who was at the Institute, also wondered why this was the case, and he said that Oppenheimer had changed, that he had become so involved with politics, he spent lots of time in Washington and so on, and then of course there was the investigation for his loyalty, and so anyway, nothing more came of that. So, at the maximum mass of a neutron star is 2.3 solar masses. It might be a little higher than that, but heavier than this, the object becomes a black hole. And as far as we know, there is no fundamental limit to the mass of black holes. It can be very small or very large, any size. But there are maybe limits to what can happen in the universe today. Okay, so there's no basic fundamental limit, but we can't think of any way to make small black holes in the universe today. And that doesn't mean the universe hasn't thought of ways, or that it might have happened early in the universe. Okay, so here's the idea. You have a huge supernova, artist's impression. And there's another supernova. This is a big one here. And makes a black hole. So what does a black hole look like? This is probably a pretty good picture of one. But we can figure out ways to detect them. Because remember how Bessel inferred that there was an object around Sirius A. Neptune was discovered because after Uranus was found in the 1780s, people found that sometimes Uranus moved a little too fast and sometimes a little too slow. And when people wondered why this is Newton's theory wrong? If you assume that Newton's theory is absolutely right, then you have to infer that there's another object further out that is sometimes ahead of Uranus and pulling on it, sometimes behind Uranus and pulling on it. And that causes the orbit of Uranus to wobble a bit. So, what was his name? I had the name yesterday. News, I think, or something like that. A French physicist and a British physicist, Adams, both came up with the idea that in order to understand the motion of Uranus, there has to be another planet. And from the motion of Uranus, we can calculate where that planet should be. And they did this almost at the same time, around 1846. And they then, both Adams and the French physicist said we should observe, we should look for this. And Adams contacted apparently more than one British observatory and they wouldn't do it. But the French physicists contacted the Berlin Observatory and told them where to look for Neptune, and they pointed to a telescope there, and within 1 hour they found Neptune. So you see, we can find invisible objects. It wasn't invisible after they pointed the telescope at it, but it was invisible before that. We can find invisible objects by looking at what they do gravitationally to things around them. So there's a recent picture of Neptune, by the way. Okay, now the other thing about black holes is they have such strong gravity that if they're near something else, they may well attract matter from that other thing. And that matter, including the light, would orbit it before falling in, and it would orbit it at extreme speeds because of this high gravity. The extreme speeds would cause huge high temperatures, which would cause X-rays to come off. And so here's a picture of what we think the surroundings of many black holes might be like. There's the black hole in the middle, but it's accreting stuff that's flowing in either from clouds or from a neighboring star and swirling around the black hole. And we might detect this swirling matter. And this swirling matter would be so hot that it would emit X-rays. And that is what we found with Cygnus X1. Cygnus X1, the designation of that star was when X-ray astronomy first began in the 1960s. The brightest X-ray source in the constellation of Cygnus was simply labeled X1. Big X-rays coming from somewhere in Cygnus. And astronomers started hunting. Where are they coming from? Trying to get close thing. They found they were coming from this star, but this star, which is a kind of a normal star, was wobbling, was moving. There was nothing there. And then it was an extremely strong X-ray source. And from that, we inferred that, that the X-rays also fluctuate in fractions of seconds. So to get a hugely strong thing to fluctuate in fractions of a second, it has to be small. So we have a small, massive thing, And that turned out to be the first black hole that was identified. And this is the picture, not the scale, of what's happening. The black hole is drawing matter away from the star. It's actually further away than this picture shows. And it's swirling around the black hole. And what happens with lots of black holes in this condition is that some of the matter swirls in and then is ejected perpendicular to the rotating material in jets. That's how that happens is a little hard to understand, but it does work.
But how could it be ejected versus all that gravitational pull?
Yeah, it's
It's a speed?
pulled in enormous speeds toward the center, and then has enough energy to
So
eject.
escape velocity is
It works, yeah. It doesn't, it's not in the black hole, it's not from in the black hole,
oh,
but it's from the regions around the black hole.
Is the fluctuation kind of periodic, or does it depend on what the black hole sucks in?
This is not periodic.
And is the jets, are those related to quasars?
Yes.
Okay.
Quasars are massive black holes. That's next time.
We don't have to come this week?
Yeah, one more question, yeah.
So, I have a problem. I think of matter as being like something solid, right?
Yeah.
Like, we're on the planet and it's the Earth is solid, right?
Yeah.
So, when it collapses, when the star collapses, what happens? Where does the matter go? How does it get? Does it get crushed or something? Is there interatomic space
Yeah.
or something? Or?
That is a difficult question because nothing can get out of the black hole, but it means we can't do anything to look into a black hole. And so what happens inside the black hole is an unknown, right? It's somehow out of the universe. It's in that black hole, but we can't do anything to test it, okay? Now, there's one slight qualification to that. Stephen Hawking showed that, well, let me put it this way. What does happen when matter goes into the black hole? The measurable mass of the black hole, that's one thing we can measure because we can see that from the outside. That increases. So the mass of the black hole increases when matter goes in it. So it's in some way in it. But where it is and what it does inside, that's an unknown.
Is it the atom, as I understand it, the atom has space between the nucleus and the circling electrons.
Yeah.
And is that space condensed? Is that what causes the matter to condense? The space between the electrons and the nucleus collapses?
I think I would not put it that way,
Okay.
that it's the collapse of an atom. Gravity is irrelevant to atoms. The electrical forces are so much bigger by many, many orders of magnitude, of many factors of 10, that that's irrelevant. This is a gravitational effect, and gravity works with big masses, and that's what's happening here.
And Roger, I mean, mass can turn into energy.
Mass can turn into energy. Mass is energy.
Exactly, I mean, you know, we use up these words. So, you know, we can't really separate atoms from that view, you know, they're not an entity necessarily.
I'm not. Yeah. What is your question exactly?
Just people people I think are getting hung up on this idea of an atom as a thing that is, you know, inviolable, doesn't change, but it does, it can turn into energy.
Yeah, any mass can turn into energy is what you're talking about.
Yeah.
But I think that isn't really what we're talking about here at this stage. Okay, we're talking about very massive objects, solar mass objects, bigger than solar masses, 10 times. That's how the black holes form. Okay, here's a picture of X-ray sources in the Milky Way. I think we found about 50 of them that are believed to be black holes, stellar-sized black holes. But there are probably several million. Because, well, I mean, look at it this way: the galaxy, our galaxy, formed probably something like 12 billion years ago. The oldest stars in our galaxy are something like 11 to 12 billion years old. And so many stars have been able to go through their evolution before we have, right? The first stars that formed, say, 10 billion years ago have already become supernovae, the massive ones. Whereas for that is the future for us. But there's lots of stars in the galaxy, 200 billion. So there's probably millions that have already gone through their evolution.
Roger, has anybody ever observed, do black holes end? I mean, is there a time at which they collapse or something happens to them?
Something happens, yeah. Okay, good question. Question is there something that happens to black holes? And for a long time it was thought no, but Stephen Hawking showed that black holes can evaporate essentially over incredibly long periods of time. And that's something I'll have to get into. But right now I just want to show they exist, right, before getting rid of them. Right? We're just. So here's another evolutionary story. Again, now this is again the same large star, but really a large star now. And becomes a red giant, becomes supernova, and then if it's massive enough to start with, over 20 solar masses, it becomes a black hole. Okay, and so the known ones that we know about, the stellar black holes, range from something like 4 solar masses, we've never seen one less massive than that, to about 30 solar masses. These are stars with masses that start out greater than 20 times and leave cores greater than 3 solar masses. Okay, now here's just a mathematical sideline for those who are interested in it. To calculate the escape velocity from something like the Earth, the velocity you need, the velocity squared, is twice the mass divided by the radius of the object times this constant g. And if you just say, what is the escape velocity of light? Then you get this formula, just substitute c squared for the v. Here, just substitute c squared here. And then you get the radius of Schwarzschild calculated. This calculation isn't really right. It's not general relativity. It's just classical physics, but it gets the right answer. So it's very close. This is the Schwarzschild radius. G times the mass of the object divided by c squared. So the size of a black hole, the Schwarzschild radius, is directly proportional to its mass. That's pretty simple. Okay, so a 3 solar mass black hole has a radius of about 9 kilometers. A 6 solar mass has about 18 kilometers. And so we know this. But, and black holes smaller than 3 to 5 solar masses may be possible. There's nothing in general relativity which prevents that, but we have never found one. And we don't know how such a thing would form in today's universe. But theorists are looking at it. Okay, so here's a summary of stellar evolution. All stars. And the three basic endpoints. So I like this thing. But this represents more than a century of astrophysical work to understand all of this. Yes.
So with all those black holes that you showed a slide, there's a lot of black holes. Does that suggest as light travels through the universe, it's actually hitting all these gravity wells and it's not going to go straight, it's going to be...
Yeah, that's true. As light goes through the universe, it will be affected by any gravity that it runs into. I don't think the effect's very big for the stellar type black holes that we see in our galaxy, but there are really, really big black holes in the universe. I mean, really big, like millions of solar masses. And they really drastically affect the light that goes by them. And we've learned how to use that. So that'll be next time.
Are they
How
the,
do we know that?
are they at the center of galaxies?
The massive black holes are at the center of galaxies. Okay, so let's put in the kind of mass ranges that we have. Okay, so some speculative ideas. We're kind of familiar with the Earth. So how big would a black hole be if the Earth became a black hole? Okay. Well, I'll leave that. I'm going to assign that as a problem for you to do if you want to. And you can email me or text me with the answer. I erase my emails and texts because I don't want to get a lot of stuff from the web. But you can look it up, and there'll be a prize for the first person to text or email me. But you don't have to do this if you don't want to.
Well, they all have my email address, so you could send it to me and I'll pick the one to send to you.
Okay, whatever.
Have you
Hey
done
Siri,
this?
how big would you
Have you
be?
done it?
I have done it. It's not too hard. Okay. So and so do it if you want to. Send it to me, and it's fun. If we get it, it'll be something that's kind of understandable because we're kind of familiar with the Earth. But if you don't want to do it, don't. I don't care if you do it or not. For 35 years, I warned students about the dire consequences of not doing the homework. So it's so relieving for me to say, I don't give it. We don't care either. But it could tell you something if you did it, okay? All right. Okay, so I'm going to end there. What time is it? Okay, and so the next time we're going to talk about black holes and galaxies. We're going to talk about the largest black holes in the universe. We're going to talk about the first images that we have of black holes, or at least of the shadows of black holes. Okay, so that'll be the subject for next time. We'll end there.